in this recording, we're going to be looking at algebraic structures. An algebraic structure is really nothing more than a set with one or two well-behaved binary operations. And in the first course in modern algebra, we typically study something called a group. And a group is a set that we'll call G with a binary operation that we'll call star that happens to have the following properties. And the properties are often referred to as the group axioms. The first property is that star is closed on G. And what that means is that if A and B both belong to G, then A star B also has to belong to G. The second thing that we're going to demand is that star is associative. And what that means is that if I take three things inside G, let's make that symbol correct, then it doesn't matter where I put the parentheses in. A star B starred with C is the same thing as A starred with B star C. The third property that all groups have to have is that they have to have an identity element. And an identity element is nothing more than something that for group theory is often called E. So there exists an E inside my set G such that E starred with A equals A starred with E equals A, and this is true for every single element inside the group G. And the fourth property that we have to have in order to have a group is that star has to have inverse elements. And what this means is that for every little a inside group G, there has to exist an element called A inverse inside group G with A star A inverse equal A star, or rather A inverse star A is equal to E. And these four things are usually referred to as the group axioms. Anything that has all four of these properties is called a group. Like I said, groups are usually the bulk of what you study in the first course in abstract algebra. Well, in this particular course, we're going to be looking at a different kind of structure, so I want to sort of look at some other algebraic structures, some of which are familiar and some of which are not. So the very first thing that we want to do is we want to talk about something called a ring. And we're going to usually write a ring as a set R with an operation that we're going to call plus and an operation that we're going to call times. So a ring is a set R that happens to have two binary operations and the two binary operations are referred to as plus and times. This one is usually called addition, and this one is multiplication. And these two operations have to have all of the following properties. So with the following properties. First of all, we want to have both plus and star, both plus and times, have to be closed. Are closed. on R. So in other words, for every pair of elements inside R, we have to have A plus B belongs to R, and we have to have A star B belongs to R. The second thing is that we want both plus and times to be associative on our set R. And what does that mean? Well, that means that for any A, B, and C inside my set R, we have to have A plus B in parentheses plus C is the same thing as A plus B plus C. And we have to have A times B times C is equal to A times B times C in parentheses that away. And let's see, the third thing is that plus has to have an identity element. And the identity element is usually called 0. So this identity element is usually called 0 sub R, meaning the 0 for the ring. And what does this mean? Well, it means that for every element inside the set R, 0R plus A has to be A plus 0R, and both of those things simply have to be A. In other words, this element 0R behaves just like the real number 0 does. Our fourth property says that the addition operation has to have inverses. And what does that mean? Well, let's see. What that means is that for every element inside R, there has to exist an element that we call minus A that also belongs to set R with A plus minus A equal minus A plus A equals the 0 element. Now, it's important to realize that we pronounce this set of symbols as minus A, or it is more properly known as the additive inverse of the element A. We don't really want to be thinking of it as -1 times A because our ring may not have a -1 element in it. And so it's important to realize that minus A is just a formal symbol for the additive inverse of the element A. The fifth property that we are going to demand is that plus must be commutative. And what that says is that for every pair of A and B elements inside the set R, A plus B has to be the same thing as B plus A. And then we have two more properties. And these two additional properties are together referred to as distributive laws. And let me make that more readable. And distributive laws, we get two of them. We get A times B plus C has to be A times B plus A times C. And we also have B plus C times A will be B times A plus C times A. Both of these are referred to as saying multiplication distributes So multiplication distributes over addition. Now, it's important to realize that these 6 properties are referred to as the ring axioms. So properties 1 through 6 are called the ring axioms, and anything that has that satisfies all 6 of these properties is indeed called a ring. There are a couple of other things that it is worth mentioning at this particular point. So I'm going to actually change color because this is a kind of a warning. The definition of ring does not demand, so it does not say whether or not star is commutative. So while all rings will have their addition being commutative, the multiplication may or may not be commutative. It is also important to understand, let's make this another warning, that the definition of a ring does not demand the existence of a multiplicative identity. It's also important to understand that the definition of a ring does not say anything, so it does not demand that multiplicative inverses exist. All of these things here, these 3 things, might be true in a ring, but they might not be true in a ring. So it's really important to understand that the definition of a ring does not demand any of those things be true. Well, there are some things that I do want to say, so let's get a basic example here. So some basic examples. Let's look at some quick examples. Let's actually do this on the next page. So some examples of rings. The very first canonical example of a ring is the set of integers under its ordinary plus and times. Now this is a ring that does happen to have a multiplicative identity, namely the number 1, and it is also a commutative ring, meaning times is commutative. But clearly, if you go back through those 6 properties, the integers under addition and multiplication satisfy them all. It also is important to realize that we have another really basic important example of rings from our previous math classes, and that would be the matrices. If I let m in n be the set of n by n matrices with let's say real entries, then if you go back through a linear algebra book, you find out that the set of matrices under matrix addition and matrix multiplication satisfies all 6 ring axioms. And so this is an example of a ring because the identity matrix, which looks like 1s on the main diagonal and 0s everywhere else, this guy is a multiplicative identity element. This particular ring, let me get my notation right. Under its plus and times is a ring with multiplicative identity. But it is not commutative. And it's not commutative because AB in general is not equal to BA when we're looking at matrix multiplication. So what we've now got are a couple of other sort of special kinds of rings that is important to be thinking about. So let me look at this idea. If I have a ring and we happen to have the existence of a special element that we usually denote by 1 sub r, with the property that 1 sub r times anything in the ring is equal to that times 1 sub r, and they're both equal to A, we first of all call the 1 a multiplicative identity, and we say that the ring itself is a ring with identity. All rings will have an additive identity. So the phrase ring with identity means that we have the existence of a multiplicative identity. On the other hand, if this particular ring is just any old ring, and it turns out that for all elements inside the ring that we know A star B is equal to B star A, then we call R a commutative ring. Now, there are rings that are commutative that don't have identity. We've already got an example of a ring that has an identity that is not commutative. So let's actually do that one kind of a basic little example here. So a commutative ring without an identity element. Well, I don't want to work very hard. I'm just going to look at the set 2 times z. And 2 times z is nothing more than 2 times n, where n is an integer. This is the set of even integers. Now, clearly, 2 times z has an addition and a times defined on it that it inherits from z. And what I want to notice is that in this structure, both plus and times are closed, because if I add two even integers, I get an even integer. If I multiply two even integers, I get an even integer. 0 is indeed even. So since 0 is equal to 2 times itself. And we also know that if I've got 2k times 2l, that's the same thing as 2l times 2k. So this guy is indeed commutative. The multiplication is commutative. And let's see, additive inverses and associativity, they're basically inherited from Z. If I look at, for an additive inverse, 2k plus minus 2k is going to add up to be 0. So we have additive inverses, and associativity, that follows from associativity in K. If I have a string, in Z, if I have a string like this, we already know that this is equal to that inside Z. So of course it's going to be true inside this particular guy. So when you put all of this together, we have all of the ring axioms satisfied, but because 1 is not inside this set, the ring 2z under plus times has no multiplicative identity element. Now, there's one final thing that I want to look at, and that happens to be some other structures that we're very, very familiar with, and so I kind of want to look at them as well. So I want to be thinking about the rational numbers under their addition and their times, and I also want to be thinking about the real numbers under their addition and their times. In both of these structures, we actually have all of the ring properties. So these are both rings, because both operations are closed, both operations are associative. We have a 0 for the additive identity. We certainly have additive inverses. We have multiplication distributes over addition. And we have a 1, so they are rings with identity. And the multiplication is commutative, so they are commutative rings with identity. But they also have another property. And they have, as I said, one more very special property. And that property is for any particular element inside of Q, or any element inside of R, with that element not being equal to 0, we have a multiplicative inverse. Namely, we have 1 over x that belongs to either Q, if x belongs to Q, and we have a 1 over x that belongs to R if x belongs to R, as long as we know that x is not 0. And so we have one more important property. And with the addition of that particular property, this extra property turns these two algebraic structures into what are called fields. So Q under its plus and times, and R under its plus n times are full-fledged fields. And fields are important because their arithmetic behaves exactly the same way that we learn about arithmetic when we're dealing with the set of rational numbers, the set of real numbers in high school mathematics. And that will be enough for this particular video.